Shall we?
Yeah.
Okay. So welcome everyone again to the AQT Colloquium. It is an absolute pleasure to have Professor Aashish Clerk with us today from the University of Chicago. Ash is a theoretical physicist and professor of molecular engineering at the University of Chicago. Ash's research focuses on understanding complex phenomena in quantum systems that are both strongly driven and subject to dissipation. It intersects the fields of condensed matter, quantum optics, and quantum information. His research has applications to various areas of quantum technology, including sensing, control, communication, and computing. Ash received his BSc from the University of Toronto and a PhD from physics from Cornell. And prior to joining the Pritzker School of Molecular Engineering, Professor Clerk served as Professor of Physics and Tier 1 Canada Research Chair at the University. And today he's going to talk about driven dissipative quantum systems and hidden time reversal symmetries. Thank you, Ash.
Great, thank you, Irfan, for the for the nice introduction and the invitation to speak here. So yeah, I'll be telling you about some theoretical work in my group, looking at a really general problem that I think is relevant to pretty much any kind of question in quantum information processing. How do we think about quantum systems that are complicated and subject both to driving, energy is being pumped in, and to dissipation? And so what I'll tell you about is a line of theoretical work in my group where we want to say things about this very general problem without making approximations. We want to say exact things about driven dissipative quantum systems that are complicated. The nonlinearities are strong, the driving is strong. There's no obvious small parameter or reason that we should be able to say something exactly. And so what I'll do in the first part of the talk is really focus on a very specific kind of problem where you have all these ingredients of strong driving, strong dissipation, nonlinearity, a kind of system that's relevant to superconducting circuits, to quantum optics, strongly driven, nonlinear coupled resonators. Okay, and I'll tell you about some work where we can really say exact things about the steady states of these systems. And I'll try to convince you this isn't just some exercise in mathematical physics and special functions. These exact solutions let us, uncover phenomena that would be really, really hard to see using other methods. So if you just did sort of brute force numerics or perturbation theory, you'd really miss some interesting phenomena, things that are measurable. So I'll tell you about how we use these exact solutions to uncover new kinds of photon blockade effects, uncover new sorts of ways to even have quantum bistability. And then depending on how time goes, in the second part of the talk, I'll ask what is maybe the deeper question: why is it that we're able to say exact things for some of these systems, right? Why does this hard problem suddenly become tractable? And I'll talk about there being a funny kind of symmetry that enables these exact descriptions. So we call it this sort of mysterious term, a hidden time reversal symmetry. But what I'll tell you about is there's a notion that you probably saw in some stat mech class, a classical notion of detailed balance. There's a quantum version of that that turns out to be really, really powerful and sort of powers all of these solutions. So that's the plan. We'll see how far we get. I think it's a nice number on the call. If there are questions, please stop and ask me. That makes these Zoom talks a little bit more interesting. Before I go on, I want to credit the people who actually did the work. So this work was really driven by two grad students in my group. So David Roberts is sort of on both these papers, dealing with both these questions, the driving force here. And then a newer grad student in my group, Andrew Lingenfelter, really made some important contributions to this second paper. Okay, so let's launch right into it. So the basic problem of a driven dissipative quantum system, right, to a theorist just boils down to this cartoon. So what do we have in this little cartoon PowerPoint figure? We have our quantum system. It's described by some honest to goodness Hermitian Hamiltonian, right? Maybe it's describing strong nonlinearities, particles that interact with one another very strongly. Then the other ingredient is we have driving. Driving can come in different forms. Maybe the Hamiltonian is time dependent, and that's describing the way we pump energy into the system. Maybe the driving comes in the form of terms in the Hamiltonian that basically create particles. Okay, so we have the driving, and then to balance the driving, we have some sort of dissipation. There's ways for energy to leak out of the system. And one of the basic questions we could ask about this mix of ingredients is, you turn all of these things on, you let the dynamics run, what is the steady state? So eventually, hopefully, the system reaches some time-independent state. That state will not be a thermal equilibrium state. It'll be some balance between how energy is going on in the dynamics from this nonlinear Hamiltonian, the dissipation. What are the properties of that steady state? Is that steady state interesting or useful? And there's a gazillion examples of concrete situations where you want to know the answer to this question. Let me give you just two examples coming from the world of superconducting circuits. So the first comes from the idea of using a quantum processor for quantum simulation. So this is an experiment from my colleagues at UChicago, Dave Schuster and John Simon, where you have an array of transmon qubits, this 1D array of transmon qubits. And the idea is to sort of simulate a bosonic or photonic Bose-Hubbard model. So particles are hopping from site to site, from qubit to qubit. There's a nonlinearity, there's an energy cost to have two photons or two particles on the same site. And then you're pumping energy into the system in a very, very special way. There's this engineered dissipation. So what they do here is they stabilize something that is akin to a state that is well known in condensed matter physics, a Mott insulator state. Here's a non-trivial driven dissipative system where the steady state is something interesting, right? So one example. Another example I won't say too much about. What else could you do with an interesting steady state? Well, maybe you could do autonomous error correction. So maybe the steady state from this mix of driving and dissipation gives me an error-protected memory. So the steady state encodes some quantum information. The driving and dissipation basically enforce the fact that if an error occurs, I go back to my desired sort of logical subspace. And there's different examples of this. There's a really beautiful experiment from Chen Wang's group at UMass Amherst that really implements this idea of dissipative or autonomous error correction in a superconducting circuit. So basically a transmon qubit that is coupling two different cavity modes, a storage mode with a really, really high Q and some dump mode. Okay, so hopefully I don't have to convince you that understanding something general about the steady states of this cartoon is interesting. To be really formal, what do I mean by the steady state? There's a density matrix that describes the system, a reduced density matrix. I want to know what that is in the long time limit. And when I say I want to understand this exactly, I don't want to do perturbation theory. I don't want to make some classical approximation, mean field theory, et cetera. So this seems like a tall order if there's no small parameter, if the interactions are large. Why would we even think there's a hope of doing this? Well, if we don't have driving and dissipation, if we just have closed systems, so complicated many-body systems described by a strongly interacting Hamiltonian, we know there are surprising examples of systems that are exactly solvable. Okay, and these tend to go under the name of integrable quantum systems, systems that can be described with what's known as the beta ansatz. But we know that these magical exact solutions are possible despite having strong nonlinearity without driving and dissipation. Could this be possible for this situation that we care about, right? This open quantum system setting. Okay, so I will not be telling you about an open system version of beta ansatz, right? Because that would be super technical and maybe not the most fun talk. I'll be telling you something that's sort of spiritually similar, that there are surprising symmetries that are not at all apparent at first glance that can still let you say non-perturbative exact things about this mix of dynamics. Okay, so that's a very, very general problem. Let's make it a whole lot concrete, something that maybe at first glance doesn't look too complicated, but still has something non-trivial there. So let's make our system now just a single bosonic mode. So single harmonic oscillator, if you want. This is the photon lowering operator. Here's the Hamiltonian of our system. So here's the harmonic oscillator, the energy of this cavity mode. We have an on-site nonlinearity. We could call this a Hubbard U. We could call this a Kerr nonlinearity. We're not going to assume this is small. Okay, so this is going to be a real nonlinearity, maybe even at the quantum level. And then our driving are these terms that I've written in red. So our driving are going to be coherent driving terms that can add 1 or 2 photons at a time. Okay, and then I have the Hermitian conjugate terms. I'm going to make things a little bit easier. And again, this is something that has been realized in many, many experiments, of course, in quantum optics, of course, in superconducting circuits. I'm going to make the problem a little bit easier. I'm going to focus on the case where this 1 photon and 2 photon driving frequencies are commensurate. So they're both detuned from the cavity resonance in equal amount. And that means I can go into a rotating frame where there's no time dependence in the Hamiltonian left. Okay, this is still a driven system because these terms here add and remove particles, either 1 at a time or 2 at a time. Okay, so the driving hasn't disappeared. It's showing up in the fact that photon number is not conserved. So that's our Hamiltonian. We have the nonlinearity, we have the driving. They could be arbitrarily strong. I'm not going to assume anything about their values. The last thing we have to describe is the dissipation, right? If we're going to put energy in, put photons into this mode, we have to give them some way to leave. So we're going to describe generically the possibility that photons can leave 1 at a time, just ordinary linear damping, or 2 at a time. And the way we'll do it is the standard way. We'll write down a Lindblad master equation. It's an equation of motion for the density matrix of our cavity mode, where this is describing my 1 photon loss. Here is that Lindblad superoperator. And maybe I have 2 photon loss processes as well. Okay, so this is my, complicated enough, but not too complicated model that I want to understand that has all of these elements. It's this Lindblad master equation whose steady state I'd like to understand without making any approximations. And again, the nonlinearity could be arbitrarily large, right? The driving could be arbitrarily large. I'm not even going to say anything about the value of these sort of damping parameters. Everyone good on what the model is? Cool, okay. Okay, so then, and again, I won't say too much about this mix of ingredients. There's been a lot of renewed interest in the world of superconducting circuits, exploiting systems like this. This is the basic building block for building bosonic error-corrected memory, right? And there's some beautiful recent experiments, for example, from Yale, that basically use this, right, to use cat states for sort of error correction. Okay, so now if you remember, or if you open up a quantum optics book from 1985, you might be a little bit confused as to why am I saying this is some interesting open problem? Problems like this, finding the exact steady state, that was done in the early 1980s. So there are these analytic solutions for the steady state density matrix of this problem that go back to sort of work by Drummond and Walls. So what do these exact solutions look like? So this is the steady state density matrix. Its matrix elements in the photon number basis. So P and Q are integers. These are Fock states. And what do you see here? You see something that is not so friendly looking. So you have an infinite sum. What are these Fs? These are hypergeometric functions. These are functions themselves that are infinite sums. Okay, so the good news is there is an exact solution here, right? There's no approximation in writing this down. The bad news is, what do you actually do with this exact solution, right? So yeah, I could put that into a computer, do this sum, make plots. But for most of us, we can't just look at an infinite sum of hypergeometric functions and immediately get physical intuition. So one of the things we want to do is actually get analytic solutions that are actually useful, that right away their form lets us say something about the phenomena we're interested in. Okay, and so that's what I'm going to do. So a lot of these models were already solved, and it was sort of seen as a fluke or some sort of tour de force. But these solutions are really, really hard to work with because their form was pretty unwieldy. So we want to get solutions that reveal phenomena. In this kind of system, what might be interesting phenomena? So I'll just hint at 2 things that we're going to actually be able to say something about. One is the idea of photon blockade. Fock states are nice, non-Gaussian states are nice. They're a quantum resource in a way that coherent states, classical states are not. If I just have a linear drive on a cavity, right, that just produces a coherent state in my cavity. That's not interesting. If I now have a large U, there's this well-known mechanism of photon blockade, that now the level spacing of the different Fock states in my cavity is nonlinear. So this drive might be resonant to take me from 0 to 1, but not resonant to go from 1 to 2. So in principle, this is a mechanism for just using a linear drive to produce a Fock state, right? An n=1 Fock state. The problem with this is you need the nonlinearity, U, which is giving you this shift of the 2 level, to be much, much bigger than the damping rate, than this 1 photon loss. Okay, so that in practice makes this a difficult mechanism to employ in a lot of systems. Wouldn't it be nice if I could get this physics having this U be much, much smaller than kappa 1? So of course that would be nice, but this picture doesn't make any sense anymore. Again, this level is broadened by whatever this kappa 1 is. I'm going to tell you a way of actually making that possible. So extremely weak nonlinearities, much smaller than single photon loss, you can get a kind of robust photon blockade. What's something else you might be interested in this kind of system? We know even classically, if you drive a nonlinear oscillator and you kind of look at the resonance curve, so the amplitude of the motion in the resonator versus the detuning of this drive versus resonance, we know we can get these resonance curves that bend over. At a particular detuning, you can have more than 1 permitted steady state classical oscillation amplitude. In the quantum case, in some cases, this can turn into what I would call a quantum bistability. So the full quantum problem, the steady state of this master equation, there's more than 1 steady state. So the 2 different oscillation amplitudes might map onto 2 different coherent state amplitudes. You could now even have steady states, right, that are superpositions of that. And again, a lot of beautiful work from Yale and other places exploiting this kind of quantum bistability, right, to actually get an error-corrected memory of sorts. Are there other ways in this kind of system to get quantum bistability, right, beyond the kind of tricks that people have already exploited? Okay, and so what I will tell you is using this exact solution, we can identify other regimes of quantum bistability. Okay, so that's the kind of phenomena that we're looking for. Let me now launch into hopefully a friendly way. How are we going to get these exact solutions that are not just exact, not just non-perturbative, but also user-friendly, right? Solutions that immediately give us some physical intuition. So the starting point is to actually go back to the simplest version of this problem. So let's get rid of the 2 photon driving, only a single photon drive. Let's get rid of the 2 photon loss. We still have this Kerr nonlinearity. So this is still not a trivial problem. This problem, there's an alternate exact solution for it beyond that crazy thing with the hypergeometric functions that is in this really beautiful paper from Kai Stanagal, Peter Rabel, and Peter Zoller. Okay, and the idea for this solution is, so I want to know the steady state that comes from this mix. There's loss, photons can leave the system. So you can't stop me from modeling this loss in whatever way I want. Because look, when photons leave, they never come back, right? That's what we mean by loss. So let's model where the photons go when they leave this resonator in a way that's convenient to theory. So how are we going to model, or how did Stanagal model the loss? Let's pretend the loss is due to a chiral waveguide. So a 1D waveguide or transmission line where photons can only go from left to right. Again, from the point of view of this cavity, this changes nothing, right? This is just saying something about the photons that are lost. They're never coming back. But now what's something we can do? Well, I can connect anything I want downstream to this fictitious chiral waveguide, because that will not impact the real cavity. So what you could imagine doing is introducing a fictitious second cavity and try to pick its properties so that in some sense, all the stuff that's emitted from cavity A goes down this waveguide and is absorbed by cavity B. And again, this will not influence anything to do with cavity A, because once the photons leave, they never come back. So the idea is, what if I could pick the properties of this fake cavity such that the entire composite system reduces to a pure state? Okay, and so if I did that, the composite system that includes this fake cavity would be in some pure state. And let's just take this to also be a cavity mode. So this is some pure state of two cavities. If I now trace out the fake cavity, I get the thing I care about, the steady state of my original cavity. So it turns out you can always do this. If you pick some amazingly complicated second system, there's always a way to make this construction work, but that's not particularly useful. The amazing thing with this problem is you don't need a very complicated fake second absorbing system. You just take the second system to, in some sense, be the mirror image of the real system. So this is also going to be a nonlinear cavity. The nonlinearity will have the opposite sign. The drive will have the opposite sign on this fake cavity. If you do that, this system relaxes to a pure steady state. You can then use that to get this exact solution. Okay, so kind of common theory trick. You add things to your problem that seem to make it worse and more complicated. We model the loss with this chiral waveguide. We introduce this fictitious second cavity. That actually makes the problem easier. It makes it easier because we get to work with a pure state. Finding this pure state turns out to be easier. That lets us get the solution that we want. Okay, and so this is for the simplest version of this problem. There's no two-photon drive, no two-photon loss. This problem never has that quantum bistability. There's no magic way of getting an amazing photon blockade effect out of this. So the thing we asked was, does some version of this trick work if we make our nonlinear cavity problem more complicated? So what if now I add the two-photon loss? What if I add the two-photon drive, so adding and removing pairs of photons at a time, a parametric drive? And what if on top of that, we're theorists, we can just keep adding things at will. Let's even add a really weird three-photon drive. So look at this thing here. There's not three A daggers, two A daggers, one A, plus Hermitian conjugate. So what's the way of thinking about this? This is a single photon drive. It's just adding one photon at the end of the day, but the amplitude depends on how many photons are still in the cavity. So why would we consider something weird like this? Well, we can still solve things if we include it. What's a more physical motivation for that? If you magically had a term like this, there's now a really, really nice way to get a photon blockade effect. So if I have a term like this, and I have an ordinary single photon drive, so just an A dagger plus A, I now have two ways in general for adding the photons. So if I start with n naught photons, and I want to go to n naught plus 1 photons, maybe it's the simple, linear, boring, single photon drive that does the work. Maybe it's this nonlinear drive. So now, because the matrix elements for this transition for the nonlinear drive depend on how many photons are already there, I can get a perfect destructive interference for going from n naught to n naught plus 1 for only one particular value of n naught. So it's almost like building a kind of wall in your Fock space that when you reach this level n naught, there's no matrix element to go any higher. So this in principle is a way to get photon blockade effects, even if the nonlinearity is very, very, very weak, because this doesn't have to do with energy detunings. This has to do with a matrix element just not being there, right? So this is actually going to be a really interesting term. It's going to be a way of getting surprisingly strong photon blockade effects. You still might not be convinced. You might be, well, this is all fine and well if you have a term like this. What I'll convince you is the physics of this term is relevant, even if it's not there. Even if you just have a Kerr cavity and this two-photon drive, you can essentially get this physics. And we have even a much more recent preprint that discusses that in more detail. Okay, so this is our final system that we wanted to solve. Nonlinear cavity, these three different driving terms, both 1 photon loss and 2 photon loss. This is more complicated than that system solved by Peter Zoller and company. This is a system that can have quantum bistability. So long story made short, despite these additional ingredients, you can still get an exact solution here. So now I need 2 chiral waveguides, one for modeling the 1 photon loss mechanism, the other for modeling the 2 photon loss mechanism. I still only need 1 fake cavity that's going to kind of absorb everything going downstream, right? And that fake cavity is going to have a Hamiltonian that's just, in a sense, the mirror image of the real cavity's Hamiltonian. So the same parameters, just with minus signs everywhere. Okay. Let me pause for a second. Is everyone still sort of on board on what the system is and why we might care about this? A thumbs up from your phone. That's always good.
I have a question.
Yeah, perfect.
Okay.
Yeah.
How important is it that the waveguide is chiral? Is it okay if some of the information gets lost to the other side?
Yeah, so this is always something I should maybe change my cartoons, because I think every time I show this to an experimentalist, they get worried because they're like, it's some theorist saying, build a chiral edge state. This is what you need to build, just this part. All of this is something I am introducing to make my job as the theorist easier. So you do not need a chiral waveguide. You just need a single cavity. You don't even really need that 2 photon loss. You just need a single nonlinear cavity that you can drive in these funny ways. This is stuff that I've introduced to let me say something exact about your system. That being said, and maybe we can get to this at the end, if you could realize these elements, then you end up with a very, very interesting state of 2 cavities. So if you're willing to do more work and actually realize the whole network, then that's a whole other level of interesting physics you can explore. But for now, let's just really focus on the things that we know people have built, and studied all the time. Just these elements. The chiral waveguides are just something I've introduced to make my life easier. Yeah, thanks for asking that. It's really important to make that clear.
Ash, is this something similar to where you embed a certain problem in the sort of the minimal Markovian kind of setup that's there? So if you made this one-way directionality that's there in a bigger system that's easier to solve, does it bear resemblance to that?
Yeah, and so it's interesting you say that. This is a version of something you might call a quantum embedding theory, right? So there are approaches to deal with strongly correlated systems that have some kind of connection to some of the ideas here. One way of thinking about it is if you really go back to, let's just, the way I even motivated the, we all know about the idea that if you have some impure density matrix, you could always purify that. You could say, oh, where did that impure density matrix come from? It came from having a larger system that was in a pure state, and I traced out half of it. So on some level, this is a way of using that idea to actually understand something about the dynamics, right? So it's a way of doing that lets me find this steady state in a very, very compact way. Everything here is Markovian, right? So there's nothing non-Markovian with or without the fake system and the chiral waveguide. That's another really interesting question. Like if I get to the end of the talk, we now have really, really general ways of understanding why these tricks work. It no longer seems like a complete fluke. So given that, we have some ideas for how you could actually use this, even if the dissipation is not Markovian.
Okay, thank you.
Cool. So I don't want to get too much into the details, but there's a really cool piece of mathematical physics that lets you, even when you reduce things to this cartoon, it's still not at first glance super obvious. So the first nice thing is it looks like you've done something worse. You first were just describing one mode. Now there's 2 modes. It still is a 1-mode problem. And the way to see that is I'm looking for a steady state of both the real cavity and the fake cavity, right? In that steady state, because I want it to be pure, there should be no photons going off to infinity to the right here in either waveguide. So what that means is both of these modes have to relax into what we call a dark state, that they cause some destructive interference such that at the end of the day, there's no fluxes going off to the right. So if I introduce these new, let's call them normal modes, the sum and differences of the real cavity, which is A, the fake cavity B, the state I'm looking for has this minus mode, A minus B, in its vacuum. So all I need to find is the state of one harmonic oscillator mode, this plus mode. So that's already a big savings. We're just looking for the pure state wave function of one mode. And then the other cool thing is there's a really old piece of mathematical physics where, in a weird way, so if I have a single harmonic oscillator, I might think about it in terms of position and momentum or in terms of quadratures. We're all used to thinking about phase space representations, the Wigner function, the Q function. There's a way of actually having a wave function in phase space. So a complex function of X and P. So if this is this state in Fock space, these are my number states of this plus mode over here. Here's my expansion coefficients. You can't stop me from making this analytic function of this complex variable Z. Think of Z as being like X plus IP. This thing here, I'm going to call a wave function, in phase space. Okay, and this is known as the Siegel-Bargmann representation. It's a Siegel-Bargmann wave function. Why do I call it that? If you take this thing and you take its modulus squared, that probability density, which is a function of X and P, that's basically your Q function. Okay, so kind of a really cute thing. This object turns out to be central to finding this solution. The exact solution tells you what this wave function in phase space is. That directly has a physical meaning. That's directly tied to the form of the steady state density matrix. Okay, so long story made short, what do we get out of this exact solution? Again, we're trying to understand the steady state density matrix of cavity A. That is not going to be pure in general. We get a very nice picture for what controls that steady state density matrix. There's a sort of pure state of a single mode that controls the steady state you're after. And there's an even nice cartoon picture. So the thing I care about is the steady state of cavity A. You could imagine that as being the output of a 50-50 beam splitter. What goes into that 50-50 beam splitter? It's this funny pure state wave function of this plus mode that we're going to find mixed with vacuum. Okay, so there's a really special structure of the steady states of these problems, right? Everything is controlled by some pure state wave function. So borrowing some terminology from condensed matter, we could call this a parent state that controls the state that we're after. And again, this state here, which I can think of.
What happens if your plus minus symmetry is not exact? Do you approach phi plus after a long time, but then deviate eventually?
Right, so one thing is, remember, all of this is an abstraction I put into the problem. So I have put things in to guarantee, right, this minus mode completely decouples.
No, yeah, I understand.
Yeah.
Like,
Yeah.
Because of the symmetry, that's exact.
Yeah, but that symmetry is something I had the choice to put in.
But
because my goal is to solve for cavity A, I'm always going to put that into the problem. If I don't do that, it's an interesting question, but that's getting away from, what my ultimate goal was. Does that make sense?
Yes.
Right, and so one little insight that comes out of this is if you want to understand things about the steady state, there's actually a pure state wave function that controls it. That Siegel-Bargmann wave function directly gives you the Wigner function of the physical cavity A state. On some level, that's depressing because the Wigner function now is the modulus squared, okay, up to some factor of the Siegel-Bargmann wave function. So the Wigner function is always positive definite. This state, though, might be some really, really crazy non-Gaussian pure state. So that means another way of looking at cavity A in phase space looks non-classical, looks singular. So for those of you who know your quantum optics terminology, the P function for the steady state of this system is singular. So that's another insight that comes out of this. Is the steady state quantum or is it classical? It's sort of in between. The Wigner function is completely positive definite and well-defined, that's guaranteed. The P function is not something you can think of as a good probability distribution. Okay, so I do want to get to a little bit about why these methods work. Let me just really quickly try to tell you the phenomenology that comes out of the steady state of this exact solution. Okay, so the bad news is I still have a special function, but it's better than that original solution. This Siegel-Bargmann wave function is now just one hypergeometric function, so I would call that progress. The really important thing, though, is there's really just two dimensionless parameters that control all of the physics in this problem, okay? And I'm going to just consider the case where lambda3 is 0 to keep things simple. So there's a parameter R1, right, that knows about the detuning of my drives and the ratio of the 1-photon drive and the 2-photon drive. And there's a dimensionless parameter R2 that only knows about the drive detuning. So here is a... Yeah, go ahead.
Sorry, the 1F1, this is a confluent hypergeometric function, the ones that are sort of related to the Euler function.
That's right. Yeah, it's a confluent hypergeometric function. So it's sort of a, it's a kind of modified exponential series.
Yeah, I mean, you get that in the hydrogen atom, right?
Yeah, exactly. No, exactly. You're right. So the way this ultimately comes up is there's a recursion relation that you've already seen in the hydrogen atom problem.
Okay, very good. Thank you.
You've definitely been teaching your quantum mechanics classes. You're fine. Very good.
I'm writing the book. Okay.
So this is almost the take-home message. This entire model boils down to a phase diagram in terms of two dimensionless parameters. The lines and the crosses are the interesting points. So anytime one of these parameters is tuned to an integer, that's either the horizontal or the vertical lines, something interesting happens. You either get a kind of photon blockade phenomena, which I'll tell you more about in a second, or a photon anti-blockade phenomena. Anytime that those lines cross where these are both integers and R2 is bigger than R1, so that's these dark red crosses, that's a new kind of near quantum bistability. So all the great cat state bistability that people at Yale have been studying, that's this point here. The exact solution lets you identify many, many more points in parameter space where you have some of that bistability physics. So let me just briefly tell you, what do I mean by all of these new photon blockade points? And why was I claiming you don't need strong nonlinearity to see this? So how would you actually, like, imagine you tried to take a cut through this phase diagram, right? So imagine I wanted to see what happens when I tune this R1 point. I want it to go between these special values that give me a blockade. So this is plotting in the steady state of our system, the average photon number in the cavity as a function of the 1-photon drive amplitude, where I keep everything else fixed. And there's no lambda3, there's no 2-photon loss. So as you vary the single photon drive, you're varying this dimensionless parameter R1. Okay, and then what you see is at very special points, there's a sudden incredibly sharp drop in the average photon number. And these points correspond exactly to when this parameter is an integer. And these points don't have 0 width. If you really zoom in, these features have a width. The solid lines are the exact solution. The diamonds are just master equation numerics to make sure we didn't mess something up. And so these sharp suppressions of average photon number at very, very special, if you want, ratios of the two drives, that's my generalized photon blockade effect. So why do I call that photon blockade? Well, at these points, what you basically have is a completely blockaded state. So a state that has photon numbers up to some threshold and then no probability for higher photon numbers. It's that state displaced in phase space. Okay, so really, I'll just describe this quickly. Here's our entire model. If you just displace it, so if you take all of your lowering operators, add an alpha to it, in a displaced frame, if this thing is an integer, you basically get that lambda3 I was talking about. So this has no lambda3. You displace, the care generates this A dagger, A term. If you pick this parameter tuning, it's exactly the setup for this blockade. There's no matrix element to go from n0 photons to n0 plus 1 photons. Okay, so if you're interested in sort of more, something we're kind of excited about, more details on how to use this to get photon blockade, take a look at this preprint. The basic idea is this is a mechanism where even if this U is much, much smaller than kappa 1, if you have a 2-photon drive in the system, in a displaced frame, you can get a perfectly blockaded state, right? You can actually even do a level of kind of universal control within that blockaded subspace, only using incredibly weak nonlinearities. And again, I would say this is a virtue of the exact solution. Once you understand the mechanism, you can understand it in different ways. This just pops out of that exact solution. Okay, so what I want to do is maybe in the last 10 minutes or something, is maybe get to the bigger picture question, and even maybe start to think about moving beyond these systems. Why are we able to solve this system, right? U is not small. There's not some obvious symmetry if you stare at this, and we have stared at this for a long time, that aha, the symmetry is somehow making this solvable. You can add some other innocuous looking terms, right? So this lambda3 term, wherever it went, right? This A dagger, A plus conjugate, that was fine. You might think all cubic terms are fine. Why not this, right? If you add that, this trick no longer works. You can't solve the system. So it's not something like 3-photon terms are fine, but things stop there. So why are we able to get solutions? If we understood that, maybe we could do this for other systems. Maybe we could even do it for systems that are not bosonic. Okay, and the idea that we've sort of come on is the symmetry we need to think about is one that we're used to thinking about in other contexts. We need to think about time reversal symmetry. We know what that means classically, right? You run the movie backwards, right? You both reverse time, you flip momenta. We know what that means quantum mechanically for closed systems, right? Maybe in Irfan's class even, you learn about an anti-unitary operator T that sort of is associated with time reversal quantum mechanically. Things are a little bit more complicated here because we have a dissipative system, right? So even classically, if I have dissipation, simply running the movie backwards, that's not a good way of thinking about time reversal symmetry. Because if I have damping, the energy will flow away to 0. I can tell forward time from reverse time. So how do you think about time reversal symmetry classically in a dissipative context? And this is getting to this idea of detailed balance. Here's a kind of classical, let's call it dissipative or stochastic system. The classical system can be in one of these 3, let's call them microstates. There are probabilities to be in those different states. You could imagine having transitions between those states. So everything is classical here. You might describe this system with this classical master equation with transition rates between those systems. You could imagine finding the steady state of this equation, right? So the time-independent solution of these probabilities, what I'm calling P infinity. The notion of microscopic reversibility of the dynamics, that becomes the idea of detailed balance. So that's saying in the steady state, the way that sort of time reversal symmetry manifests itself is there's a balancing of probability fluxes. Okay, so this is like the probability flux in going from state I to state J. This is sort of the reverse thing. So these tildes are supposed to be whatever your notion of time reversal is. Ignore the tildes for now, the simplest case. It's just telling you in the steady state, the flux of probability from 1 to 2 balances the flux from 2 to 1. It's telling you in the steady state, there's not some kind of stable circulating current. All of this is classical. That immediately implies this kind of correlation function symmetry in the steady state. So if you measure two quantities, one at time 0, one at time t, if you move the t to the b quantity, and the tilde is do a time reversal if you have to, these things are the same. Sometimes this is called an Onsager-like time symmetry. So this is all classical detailed balance. What is quantum detailed balance? So if you Google that, you will get a million different, definitions, right? One standard way in quantum optics to define detailed balance. Well, look, this is not a good definition. Here's my quantum master equation. I don't just have transition rates, I have coherent dynamics. So it's hard to use this definition, but this is a good definition, right? Quantum mechanically, I could calculate correlation functions. I could demand that I have this time symmetry, right? Whether the t is on the A or on the B, I get the same answer. And that's a definition of detailed balance in the quantum regime that I would say is the most common one. And it goes back to this work from Agrawal and Carmichael in the 70s. So what do we want? We want a symmetry that lets us say something about non-trivial systems. The sad thing is, if you insist on this symmetry in a quantum system, your quantum system on some level has a pretty boring steady state. So the only steady states that are possible if you have this symmetry are states that have no coherences between energy eigenstates. So I have a Hamiltonian here. The idea is the steady state I get from my master equation, if it's going to have detailed balance according to this definition, it's diagonal in the energy eigenstate basis. So that means some of the simplest dissipative systems you can think about, a quantum driven harmonic oscillator, a Rabi driven qubit, they don't have this symmetry. Okay, so what I'm going to tell you about is a weirder symmetry that turns out to be the magic that fuels our exact solutions. Okay, and I don't want to go too over time. Let me start by writing the most convoluted definition of classical detailed balance you've ever seen. So hopefully this is familiar, this is familiar. Here's a completely equivalent construction. So here is my classical system, transition rates, a classical master equation describing transition between these systems. Let me double the system. So here's another classical system that has the same microstates. It has no transitions whatsoever. So this system B, nothing ever changes. And now this joint system, A, still have transitions like we had before, B, nothing happens. Let's start the joint system in this funny correlated state. So system A is in the steady state of that classical master equation. System B is just perfectly correlated. So if system A was in state 1, system B is in the time reverse partner of that. Okay, so really, really weird construction. If you do this and you now evolve the system, only A evolves, detailed balance can also be defined in this way. If you measure something on A at time t, measure something on B at time 0, you get the same answer if you flip the x's and the y's. Okay, so there's a completely convoluted way of formulating classical detailed balance with this doubled system. We'd never do this classically because there's no reason. It doesn't tell us anything more than these definitions. This is equivalent. So why am I telling you this? I can now generalize this to something quantum mechanical and get something new. So quantum mechanically, I now have a master equation describing my system A. It has some steady state, right? Which might not be diagonal in the energy eigenstate basis. This idea of having a doubled system prepared in a correlated state, I could prepare an entangled state of a doubled system. So now I have this B system, which has the same Hilbert space or dimensionality as the A system. And this is now a correlated state of a doubled system. And even in this classical construction, the doubled system, I'm going to do some time reversal operation to get its states. So the idea is this is a correlated system or a correlated state of my real system, a copy of it. It depends on some choice of an anti-unitary time reversal operator. And now I'm going to define time reversal symmetry if I've picked this T in the right way to sort of make this state special. And it's basically just jumping to the final answer. What do I want to do? I am going to say that my system has a hidden time reversal symmetry or satisfies a useful notion of quantum detailed balance. If I prepare the real system and the fake system in this state, and now if I measure quantum mechanically correlation functions between the A and the B system, well, if I always have this equality, if I flip the X's and Y's, and I always get the same thing, I will define that to be quantum detailed balance. Okay, so let me pause here. This is, again, no one can stop me from defining things in any way I want. I've tried to copy something that classically, this is just another funny way of thinking about classical detailed balance. This is a convoluted way of sort of turning that quantum mechanical. This is sort of a famous entangled state in a lot of contexts. This is known as a thermofield doubled state. So here I'm defining a notion of time reversal, some t being interesting. So why would I go through this? And this is this notion, this definition of quantum detailed balance, that's in the mathematical physics literature. So our definition here isn't a new one. What's new is we can actually show that this definition is useful, right? So let me just even jump to the kind of main thing. If your system satisfies this definition, then you're guaranteed to be able to find one of these exact solutions. So that is this trick of doubling your system, bringing in these chiral waveguides, picking this fake auxiliary system in a simple way, using this cascaded system to find in a simple way a steady state, that's guaranteed to work. So the ability to find simple exact solutions is connected to the existence of some kind of hidden time reversal symmetry. And I call it hidden because the simplest way of identifying it is you'd have to build two systems to see this correlation function symmetry. Okay, so time is short. The one little good news I will tell you, if your system happens to have that hidden time reversal symmetry and you only have a single system, there are special correlation functions you can measure that are guaranteed to be symmetric in time. So not all correlation functions will be time symmetric. So this is, again, one of our driven care systems. If you take some correlation function, the x squared of t, p squared of 0 correlation function, no time symmetry according to that 1970s style quantum detailed balance, you don't have quantum detailed balance. The fact that our definition holds, the fact that this is exactly solvable, you have some correlation function symmetry. So the upshot is you could measure the presence of this symmetry even with just a single system, right? Going back to Gerwin's question, you don't need to build the system with the chiral waveguides. The other thing is you can have like phase transitions. You can have this symmetry broken at some finite temperature, right? So this idea, we're really kind of excited about it. It underlies these exact solutions. It's a new kind of symmetry to sort of explore in the context of driven dissipative systems. So I'm out of time. I think we're scratching the surface of what we can do with this. This is not just limited to single nonlinear oscillators. This is stuff we hope to publish soon or write up soon. It holds up in sort of lattice systems. It can hold up with things that aren't just involving bosons. We really think it's a really, really general way of looking at things. I will flash up my conclusions. Thank you for your time, and I will stop here. Thank you.
Thank you, Ash. That's a clap for our speaker. You'll have to do with the little emojis.
Yeah, exactly. No, it's always shows that people are still there in a way. That's always a good thing. So yeah.
Good questions for our speaker. Please go ahead and unmute.
I actually have a question. So at some point, you mentioned very briefly on the first part, you mentioned the unconventional photon blockade, right? And I didn't catch fully like.
Yeah, I didn't actually say anything about that. Yeah, that's a really crucial thing, right? So I just kind of said here, very different, right? So if you know what this unconventional photon blockade is, it might seem like it has similar ingredients, right? And we have a paper that sort of describes that you can also get that using a 1-photon drive and a 2-photon drive and a U. The unconventional photon blockade mechanism, it can generate states where the G2 function goes to 0, but the states you generate are always Gaussian, right? So they're completely Gaussian states. They never have a true blockade in the sense there is a probability for having 2 photons, 3 photons, 4 photons. It's just a Gaussian state where the probability of having 2 photons versus the probability of having 1 photon is a lot lower than a coherent state. This mechanism is different because it's a true blockade. There is 0 probability for having more photons. The other thing with unconventional photon blockade, if you want a really small G2, the average photon number also goes to 0, right? So these states are very dim. There's no constraint on this mechanism because it's a wall in Hilbert space. So it's almost like you've turned your cavity into a qubit despite the U being incredibly small, right?
So for the unconventional photon blockade, like you have to design very precisely the ratio of all the parameters, and that was experimentally challenging. And it seems that you have the same kind of.
Absolutely, right. And so that's actually, I can flash up the reference again. You know, we're trading one hard thing for another, right? There's, you know, the usual no free lunch theorem still holds. So look, you don't need a giant U, but you do need the ability to balance the amplitude of these drives really well. So in this preprint, we go through, you know, quasi-realistic numbers. We look at the, you know, what happens if you don't match things perfectly? What if you have different kinds of imperfections? One of the nice things is, if you're a little bit more modest and you say, I don't really need the blockade at infinite time. I just want the blockade to last for a really long time. So then a mismatch in these parameters means that there's a long time scale over which you escape this blockaded subspace, you go to higher photon numbers, but that can still be really long enough for you to do something interesting. So there is some robustness to those parameters not being matched well. But yeah, I'm not claiming this is super easy, right? Okay. The weak you need control over these amplitudes, yeah.
Okay, thank you very much.
You're welcome.
Other questions for Ash? Let me ask one, Ash. So on the same topic of this photon blockade, is it possible to sort of use this kind of technology or this kind of engineering where you have a driven cavity with some kind of dissipation and some kind of tunable filter, right? Where we can sort of change, for example, somehow, you know, some kind of more exotic Purcell filter or some other coupling mechanism between qubits and what have you.
Yeah, it's an interesting idea. I think here all of the focus has really been on like the nonlinear physics, right? But you know, if you thought about something more exotic, like a photon number sieve, right, where you have some state, and then you want to sort of truncate it, right? You want to, or even do something more selective. Yeah, it does seem like some of these, you know, some of this physics might let you do things like that without needing as large a nonlinearity or as complicated a nonlinearity as you might you know, have thought. So that's an interesting thing we should think about more.
Yeah, so if we can get more functionality by putting more, you know, precision on the drives, which seems to be a more reasonable, you know, thing to do.
Yeah, I think that's a really good way of saying it. That like this is a way of trading off. Like you no longer need a really large nonlinearity if you're able to control these kind of surprising interference properties well.
Yeah.
And in a lot of systems, that might not be such a terrible trade-off.
No, it might be quite useful indeed. Okay, any other questions for Ash? All right, so we are 4 minutes or 5 minutes past the hour.